We get two sheet votes first. Yes. All right, it's 4:30. Let's go and get started. All right, so thank you guys. I know it's a bit awkward to have an exam and then have a lecture right after, but the show must go on. A little bit kind of just this function of the summer session. So the exams, luckily this is the only class I'm teaching this summer. So I will probably have them graded by Tuesday. I plan to do some grading tomorrow, do a couple of meetings tomorrow, and then probably finish them up on Monday. So should be able to grade them pretty quick and get them back to you guys pretty quickly. Okay. All right. And so the topic for today is we're just going to be building off kind of what we went over yesterday. So yesterday we introduced this concept of Reynolds transport theorem, or RTT. So today is going to be actually mostly examples. So I have 4 examples lined up for today. They're all kind of illustrating different things for Reynolds transport theorem. We'll actually see an example of a moving control volume, one for a deforming control volume. Trust me, they're less intimidating than you think. And then we'll set ourselves up where on next Tuesday we'll start talking about conservation of momentum, which is where things actually get really interesting with fluids. Okay. Okay, all right. And so any questions I can answer? I know we just took the exam, but any questions about transport or anything we talked about yesterday before we get started? Okay, all right. So let's go ahead and get started. All right, so today is kind of part 1 of what I consider to be control volume analysis. Okay. So, like I mentioned yesterday, this is kind of where the class really kind of starts to take off. This is where problems get a bit more complex, but we can do a lot more interesting things now as well. Okay. All right, and so the kind of this whole central theme of today and Tuesday and likely next Wednesday as well is that we'll be applying and drawing these control volumes and using that as kind of the framework for applying our basic conservation laws to these systems. All right, and so in that sense, this part of fluid mechanics is not all that different from what you've learned in classical mechanics, because all the equations and all the concepts that you understand from classical mechanics, solid mechanics, statics, dynamics, they're all born essentially from conservation laws, conservation of mass, conservation of momentum, conservation of energy, right? So fluids all follow the same rules. It's just that mathematically the way that we analyze them has to be different, just because of how fluid mechanics just behaves differently from solids. Okay. Um, and so with that, this will be kind of really the catalyst for us to actually start to look at some really interesting problems in fluids. All right, so the way this is structured is that I've kind of organized this according to the conservation law. So today we're starting with conservation of mass. The next one on the top, no, next one on the docket will be conservation of momentum. So that's what we're going to cover next Tuesday. We'll probably also cover conservation of energy next Tuesday as well. And then, depending on, if we have time or not, we'll do conservation of angular momentum. But angular momentum is it's interesting. It's cool. But it's one of those things that I think just adds a lot of complexity to class that already has a lot of complexity, but may not have a lot of really practical applications. And so we'll see how far we get. We may stop after conservation of energy, but we'll try to make that decision. Okay. Okay, so with that, let's go ahead and go on to conservation of mass. Okay. So today's lecture is going to start the same as the next lecture. So we're going to start with our general Reynolds transport theory. So we'll write the general form first, and then we'll apply conservation of mass to it by plugging in for B. Okay. All right, and so I'm gonna write the kind of the secondary form of Reynolds transport, just because this is the one that's more traditional. Right? All right, so in this form, we have the production or the consumption term on the left-hand side. On the right-hand side, we have our accumulation term and our flux term. So this first term here is the accumulation slash depletion term. And this term here is our inflow slash outflow term. Okay. Which, if you recall from yesterday, we also called that our flux term. Okay. All right, so this Reynolds transport, this is true for any number of different quantities, right? So in this scenario here, or in this equation, big B or capital B, that refers to some extensive property in the fluid, and little b is its intensive version. Okay, so for conservation of mass, yeah. So for conservation of mass, we're essentially going to make two substitutions and one application with it. Okay? So first, right? So the first substitution that we're going to make is we're going to set our extensive property capital B equal to mass, okay? Because that is what we're applying it to, right? That means little b, which remember the way that we define little b here is big B divided by mass. And so mass divided by mass is, in this case, is just 1. Okay. Right. The other thing that we're going to do is just like we did with the last example of class yesterday, is we make note that in a given system, right? So remember, a system refers to a fixed amount of mass, right? Because mass can neither be created nor destroyed, we can basically eliminate that derivative term on the left-hand side. Okay, so if we make those substitutions, then we get a more simplified version of conservation of mass, so Reynolds transport theorem. Right, so we plug these in, we get 0 is equal to partial t of integral rho dv plus integral rho v dot n hat v. So this equation right here, this is our Reynolds transport theorem for conservation of mass. So it's going to seem like a little bit deja vu, just because we just had this lecture yesterday. But you know this the reason I kind of go over this again is because normally this set of lecture note comes a week after what we did yesterday. But you know I know we just did this yesterday, but you know, but I know probably yesterday everyone's mind was on the midterm, so it's good to kind of refresh this stuff. All right, so you know this is kind of the mathematical version of conservation of mass, but there's kind of a more plain, simple way to kind of state this, right? So because mass can neither be created nor destroyed, right? Basically here we have a balance between the amount of inflow, outflow that comes into the domain, as well as the accumulation. Okay. And so another way to kind of state this equation, kind of in plain terms, is to say that, you know, the only way for there to be an accumulation or depletion of mass, of fluid mass within a system is if there is an imbalance of inflow and outflow. Right, so if mass is accumulating, so if water is accumulating in your system, that means there's more inflow of mass coming in than there is outflow, right? Whereas if there's water or fluid depleting from your control volume, that means there's more outflow than inflow, right? It sounds very simple, I think, when you say it like that. But that's, you know, just kind of mathematics. Okay? Another way to kind of state this, that is useful to kind of think about when you're doing these problems, where if you have steady state conditions, in other words, you know, mass is neither accumulating nor depleting in your system. So we're gonna do some example problems today where we are going to look at steady state conditions, right? So steady, all that means is that anytime you have a time derivative, that term is going to be equal to zero. So partial t equal to zero. Okay. Right, and so that accumulation term, right? Because the accumulation term is the only term in our equation here that has a time derivative. If that term is equal to zero, that means all of your inflows and outflows must be perfectly balanced. Okay. All right, so we're going to look at both of these types of scenarios today. So we're going to look at unsteady situations where there's an accumulation, and we'll also look at steady conditions where all the inflows and outflows would be balanced. Okay, so that's kind of the central, this is kind of the central equation that we're going to be working with today. And we're just going to be, in basically all four examples that we're doing today, we're going to be applying this equation to all those different scenarios. Okay. All right, any questions on this so far? Okay. All right. So before we jump into our first example, let's go over just a few more terms here. So to kind of help simplify this, and also just to kind of give you some additional context, because some problems will give you this, let's introduce the concept of a mass flow rate. All right. So the mass flow rate is a quantity that tells you how much fluid mass is entering or is flowing past a certain region per time. Okay. Yeah, yeah. So that's exactly what that measures. Yeah, so mass flow rate is a very common metric that's used in fluid mechanics, right? It's almost like parallel to the volumetric flow rate. So volumetric flow rate, remember that's something we introduced with Bernoulli's equation. In fact, transferring between them is actually very simple. Okay, so the mass flow rate, often we give that the symbol m dot. Okay? M being mass, and the dot there telling you that it's a rate of change. Okay, is equal to. You take the velocity of the flow, you multiply that by the area, okay, cross-sectional area, and then you multiply that by the density. So it's a product of those three things. Okay. And so the dimensions, okay, so if you look at the dimensions of the mass flow rate, that's equal to mass over time. Right? Or if you want to look at its SI units, the traditional SI units for mass flow rate is kilograms per second. All right, and so in these problems, that you'll see, we'll either be computing mass flow rate or it's something that will be given to us in the problem as a parameter. Okay. All right. So why am I bringing this up? Right. So this combination of variables here, the velocity, the area, and the density, this shows up very commonly in conservation of mass type of problems, or whenever you're computing conservation of mass for a system. Okay. So if you look at our Reynolds transport, right? So in fact, if you look at this last term right here, our flux term, okay? Right. So if we look at our integral rho times velocity dot product with normal vector dA, okay? Right. When you evaluate this term for a given control volume, given the fact that oftentimes density is going to be a constant, we're going to assume velocity is a constant. We do have to account for the sign, so don't forget that. Okay. And then eventually, when we integrate this, we're going to get the area as well. Okay. Right. So when we evaluate this, we usually get the product of rho times velocity times the area. Okay. Which is exactly the mass flow rate, right? So this term right here, usually when you evaluate this, you obtain a mass flow rate. Okay, so when you're doing these problems, sometimes the problem will give you an inlet mass flow rate or an outlet mass flow rate. Don't be tripped up by that terminology. Essentially, they're giving you the amount of inflow that you can plug into Reynolds transport theorem. Okay. Okay. And so that means that, we can actually take this term here and we can rewrite it in a more convenient form. Okay, so I would say, when people are kind of first starting out, this is your first time using Reynolds transform, people kind of like this form because it's a bit more intuitive. Okay. And so when you evaluate this term here, you end up with, and this form here is general. So this will work for systems with multiple inlets or multiple outlets. Okay. Right. And so this is going to equal to the sum of the mass flow rates at all of the outflows minus the summation of the mass flow rates at all of the inflows. Okay. Well, remember, remember the sign convention. And so because of this dot product here, okay, so this is something that we talked about at the end of lecture yesterday, right? So for outflows, outflows being sections of your control volume where your velocity and your normal vector are totally aligned, so they're parallel and they face the same direction. E dot n is positive, greater than 0. Whereas for inflows, v dot n is actually less than 0, right? Because the velocity and normal vector there are not aligned in the same direction. Okay, so that's where the sign convention comes from. So the fact that we sum the mass flows at the outflow, those are positive, and we subtract all the mass flows at the inlets, those are negative. That comes directly from the sign convention of the dot product. Okay. Okay, so if it's more useful, or if it's easier to evaluate this way, you can definitely use this form here. Just to kind of plug in. This one's a little bit easier to use than looking at the unit. Okay. All right. Any questions on this? Okay. One final point before we jump into an example. Right. So in everything that we're going to do in the control volume section, we are essentially making the assumption that the velocity is uniform across a given area. Okay, so that not only goes for today, but it goes for next week as well. Okay. So everywhere that we're looking at a velocity, we're assuming that the velocity is constant across the whole area. Okay. And that's just kind of for ease of calculations, right? Otherwise, you can do it for non-uniform velocities, but for now we are going to just assume that that's the case. Okay. But for situations, especially true for situations where viscosity plays a big role, this is not necessarily true. So one thing we'll learn, after the control volume unit here, once we start to get to Navier-Stokes, is that the velocity profile or the velocity field actually does change with space. Okay. So one of the most iconic velocity profiles that we'll learn and kind of go over is what's known as the parabolic profile, right? And so if you have flow in a pipe or if you have flow kind of in a constrained kind of between walls, right? What tends to happen is that the velocity forms this parabolic shape where it's maximum at the middle, in the middle of the pipe, but actually goes to zero at the walls. Something like that. Right. So velocity is no longer is so velocity is not a constant value. It actually varies with space. Okay. So we're ignoring that. We're not considering differences in space. Okay. Right. So what we're doing instead, just so that you're aware, is we're assuming that across a cross-sectional area, we're assuming the velocity is constant across the entire area. Right. So it looks something more like this. Right. So we just have a single value of velocity that we can just kind of plug right into the Reynolds transport theorem. Right. Okay. We're just doing it implicitly, so this is not something that you have to be explicitly aware of, as you're kind of doing this problems. But I did want to mention it just because it is actually a very important assumption that we're making. Okay. But you can reconcile these. And so even for situations where you have a parabolic profile or you have a varying profile, you can still use control volume analysis. In fact, this is actually used quite often. And so in those situations, instead of taking the whole profile, you're instead going to take the average velocity. Okay, so just kind of be aware of that, right? And so the whole kind of upside to that is that when we evaluate this integral here, right? Normally, what makes this integral difficult to evaluate is the fact this velocity can change across that area, right? And so if your velocity has any kind of dependence on space, then that integral becomes a lot more difficult to evaluate. But if we assume that this velocity is a constant, right? Of course, accounting for the sign, whether we're at an inflow or an outflow, then this integral becomes easy to evaluate, and we can actually use the form that's on the right here, the sum of the mass flow rates at the outflow minus the mass flow rates at the inflow. Okay. Okay, any questions on that before we jump into an example? Okay, all right, so let's go ahead and do our first example here. Okay, so with this first example, let's do control volume analysis of an HVAC system, right? So we're going to look at a problem where we are forced to, or we want to design a system to ventilate a room. Okay, so let's say that we have a certain room in a certain building, and its dimensions are 10 feet by 6 feet by 6 feet. Okay. So actually, I guess it doesn't really matter for this problem. Let's make 10 feet the height. That probably makes the most sense because otherwise, if you're over 6 foot tall, you wouldn't be comfortable. Okay. So let's say the height of this room is 10 feet. The width of the room is 6 foot. And the depth of the room also 6 foot. Okay. So if you get into HVAC engineering, you'll know that ventilating a confined space is something that's very, very important. Because unlike the great outdoors where when you breathe out, your carbon dioxide just goes into the atmosphere. If you don't have proper ventilation in a confined space, whatever carbon dioxide you breathe out stays in the room, right? And so which is bad because we as humans we need oxygen in order to survive. Okay. Ventilation is especially important for applications where maybe you're doing some type of work in this room where particulates are going to be in the air, and so you need to ventilate it so that those particulates don't cause people breathing problems. Okay, so one common application for this, that I've experienced a little bit myself, is that if you work on any kind of industrial paint applications where you're spray painting a lot of stuff that puts a lot of particulates in the air, right? And so you really need a room with proper ventilation in order to perform that work. Otherwise, you're going to be breathing in paint particles, and it's going to cause a bunch of health problems. Okay. So one of the safety regulations for this room states that every 3 minutes, all the air in the room has to be refreshed, right? And so we have to basically pump in air to the room and get air out of the room such that there's every 3 minutes you have a fresh amount of air. I have a funny story about this. It has nothing to do with fluids, but one of my first jobs as an intern at an engineering company. So the company I worked for, they did experiments in these things called vacuum chambers. And so if you want to basically test, maybe satellites or devices that are designed to go in space, and you can do it in the absence of oxygen. We've designed these things called vacuum chambers where it's a confined space, but they design it in a way so that you can suck out all of the air in the room, so you can kind of simulate space conditions, right? So my first job as an intern was to clean the vacuum chamber every day. So I would come to work. I would take a bottle of isopropyl alcohol and some wipes and just wipe down every surface on side the vacuum chamber because that vacuum chamber has to be squeaky clean. Because if you have any dust or any kind of particulates in there, if they get into the pumps, then that's probably $100,000 fix that you have to do. So as a joke, in my second week of the job, the contractors thought it would be funny to lock me in the vacuum chamber. So I was in there and just I was cleaning the far end, and then just all of a sudden I feel or I hear the door close, and yeah, that was my first time experiencing a panic attack, which was not fun, but I'm alive, I think. And so, thankfully it's a funny story at this point. But yeah, I don't like confined spaces, and so this is this example is a little bit triggering for me. Okay. Anyway, okay, back to the example here. All right, and so to ventilate this room, normally you wouldn't design a room like this, but we have just a single inlet and a single outlet. Okay, so we have one inlet hose coming in. And so the diameter of the inlet hose here is 8 inches. So the inlet hose is basically pumping fresh air into the room. Okay. But we also need a ventilation shaft as well. So that air needs to go somewhere else. So we have an outlet hose as well. Right, so this is our outlet, and our outlet hose only has a diameter of 4 inches. Okay, so in this problem here, based on everything that we know, let's compute. let's compute the flow rate of air that's necessary to satisfy these safety conditions. Okay. And uh, B, assuming that the velocities at the inlet hose and outlet hose are uniform, right? So we're not considering any spatial variation in the velocity. Let's compute the average velocity of air at the inlet and the average velocity of air at the outlet. Okay, so we have a two-part problem, but you'll see that this problem is actually fairly straightforward. Okay? We actually barely have to apply Reynolds transport at all. Okay, so let's start with part A. So part A asks us to compute the flow rate of air. All right, so flow rate. So in this problem, it's a little bit vague, and so it just asks for the flow rate. So flow rate can either be volumetric flow rate or it can be mass flow rate. Right, so let me just refresh your memory in terms of both of those equations. In fact, they're both related just by the density as well. Right, so volumetric flow rate. Remember, we learned this variable back in Bernoulli, so we gave this the symbol Q. Okay. Q is just equal to the product of the velocity multiplied by the area. And the mass flow rate, which is what we just learned, is the density multiplied by the velocity multiplied by the area. Okay. All right, so technically we can choose either one here. For this problem here, we aren't given the density of air, although that's something you can easily look up. But because we're not given the density, let's just compute the volumetric flow rate in this case. Okay. So we want to find out, how much air we need to be pumping into this room at any given time. Okay. Okay. All right. So to solve for this, so we need to look up our safety regulations here and find out, how much air we need to pump in, right? So the safety regulations tell us that every 3 minutes, the entire volume of air in the room has to be changed out, right? So within that 3 minutes, we have to pump in enough air into the room to replace all the air that is in. Okay. All right, and so actually we have all the information that we need for this problem already, and we can do this actually without applying Reynolds transport theorem. Okay, so let's start with the volume of the room because we can actually compute that right away, right? Because we are given the room's dimensions. Okay, so the volume of the room. Okay, we're just going to take its 3 dimensions, 10 foot by 6 foot by 6 foot, and just multiply them all together. So 10 times 6 times 6. Okay. This gives us a volume of 360 cubic feet. Okay. And so we have to pump in a volume of 360 feet cubed of air into the room every 3 minutes. And so if to convert this to a flow rate, we're simply just going to divide this volume by the time that we have. Okay. Okay, so the time that we have is 3 minutes. Right, technically, you can just divide the 360 feet cubed by 3 minutes, but usually we like to work in seconds. Right, so let's convert this to seconds. So 3 minutes multiplied by 60 seconds per minute is 180 seconds. Okay. And so the volumetric flow rate in this case is 360 feet cubed divided by 180 seconds, right? And so that's pretty simple. 360 divided by 180 is just 2. And so the total amount of flow rate that we need to pump into the room at any given time is 2 feet cubed per second. Okay. Okay, so that information there will tell you usually, usually for these types of ventilation problems, you kind of need to do forced ventilation. You just can't rely on natural ventilation like in this room. So this will tell you usually the type of pump that you need in order to satisfy that condition there. Okay, any questions on this so far? Okay, good. All right. So before we get to part B, well, let's do part B, and then we can do it as we do part B. Okay. All right. So part B asks us to compute the average velocity of the air at the inlet and outlet. So let's now apply our Reynolds transport theorem to this problem. We technically don't need it. We can just by knowledge that we have a single inlet and single outlet, we actually have everything that we need. But it's good practice to apply Reynolds transport theorem. Okay. Okay. So our Reynolds transport theorem for conservation of mass, let's write out the entire expression. So we have 0 is equal to partial T of integral of the density integrated over the volume plus integral rho v dot n at d. Okay. Let's simplify this equation based on what we know from the problem, right? So we're designing this room, or I guess more specifically, we're designing the ventilation system for this room to be working under kind of persistent conditions, right? And so that means we're working under steady state. So nothing is really changing with time here because we're not, this is something that we're designing for just normal operating use. And so with that said, we can assume this term is 0. Right. So remember, anytime you're solving for systems under steady conditions, you can assume any time derivative is equal to 0. Okay. That leaves us with the following term here on the right, which is our inflow outflow term. Okay. Right. So we have 0 is equal to integral of density multiplied by the dot product of the velocity and the normal vector times dA. Okay. All right. So since we're working with a situation here where we are considering average velocity, we can replace this the form for this integral here. Okay. Let's put this in a more convenient form that we kind of discussed right before this example. So this is equal to summation of all the mass flow rates at the outlet minus the summation of all the mass flow rates at the inlet. Right. Which in this case, we only have a single inlet, we only have a single outlet, right? And so let's replace those expressions with those things. Okay. All right. So at our inlet, we only have one, right? We know that the inlet has a yes, yeah, 8-inch diameter. But let's do it in terms of area first. And so this is just going to be the product of the density multiplied by the velocity at the inlet, average velocity multiplied by the area. Okay. And then same thing for the outlet. So at the outlet, so this is equal to m dot in. The outlet, we have density multiplied by the velocity at the outlet, multiplied by area at the outlet. All right, and so we only have a single inlet, single outlet, so the summations don't really matter in this case. Okay, so if we plug those in, right, so we plug in for m dot out, we plug in for m dot in, okay, we get 0 is equal to rho v out, a out, minus rho v in, a in, okay. Right, where of course we can compute the cross-sectional areas based on the diameters that's given to us, and that's pi over 4 d squared. Okay, so we'll do that in a second. Right, so luckily for us here, just because we're under steady conditions and we have air as the working fluid all throughout, we can factor out a density and just cancel it out from our equation, so that term goes away. Okay. Let's move one of these terms over to the other side. And so this tells us, based on conservation of mass, that the velocity at the outlet multiplied by area at the outlet is equal to velocity at the inlet multiplied by area at the inlet. Okay. In other words, the volumetric flow rate of air coming in has to equal the volumetric flow rate of air going out. Okay. Remember, the product of the velocity multiplied by the area is volumetric flow rate. Okay. Question, yes.
Earlier you said we had steady conditions. Can you just remind me what was given to us in the problem? So it's snow and steady.
Yeah, no, good question. Yeah, so you'll see in the next problem an example of unsteady, but unsteady conditions would be a situation where maybe we're pumping more air in and air is accumulating inside the room, or maybe it's depleting inside the room. And so if you don't see any keywords of like accumulation or buildup, then you can assume it's steady conditions. Okay. All right, so volumetric flow rate in has to equal volumetric flow rate out, and convenient for us, in part A, we already computed the volumetric flow rate, right? So both of these have to equal Q, right? Which is what we saw for in part A. Okay, and so if we extrapolate from that, we can then use that information to compute our velocities, right? Because we have Q is equal to V out, A out, and Q is equal to Vn A in. Okay. Right, and then so now since we already know the volumetric flow rate for part A, it's a simple matter here to solve for V. All right, so V out in this case is equal to Q divided by A out. Where A out here, that's that we can compute that based on the diameter of the hose. Right, so this is Q divided by pi over 4 D out squared. Okay. We plug in for that, we get 22.92 feet per second. And then U in or V in is equal to Q divided by A in, which is Q divided by pi over 4 D in squared. Okay. All right, so we plug in for that, we get 5.73 feet per second. All right. Any questions on this example here? Okay. All right. So let's do another example. Let's do another example, and this one will do one which is unsteady. Okay. So for this example here, we are going to do an example, another safety example. This time we're going to look at construction safety of work inside a trench. Okay. So let's consider a situation of a construction worker doing some road work inside a trench that's next to a busy road. And so just like any busy road, we have, lots and lots of cars coming by. The cars are, emitting a lot of these, harmful gases. One of them being carbon dioxide, CO2. Okay. Now, CO2 is more dense than air. And so what do we know from, from buoyancy is that when you have a fluid that's more dense than the surrounding air, it tends to sink or come to the bottom. Okay. In this case, that CO2 is going to sink into the trench. All right, so we have a trench like this. All right, so let's say we have a person here. Right, and so then, just by natural, natural phenomenon here, we have CO2 that's essentially coming into the trench. All right, so let me give you some dimensions here. So let's say that our trench is 10 feet wide. Let's say it is 8 foot tall. And let's say into the page, the depth we'll say is 5 feet. Okay. So let's assume that we're starting from rest conditions, right? So let's assume that the trench initially is filled with completely of just air. Okay. And let's also assume that we know the flow rate of CO2 into the trench. Okay, so let's assume that flow rate is 10 feet cubed per minute. Okay. Right, so a little different than the last problem. So this time we actually know the inflow. Okay. Also unlike the previous problem, the CO2 has nowhere to go, right? And so instead of being vented outward, so let's say that there's no outlet air or outlet vent, that CO2 is going to settle. Okay. Okay. So there's basically no way for the CO2 to escape. All right. So let's compute a couple things. Okay, so first let's compute the rate of which the height of CO2 in the trench changes with time. So of course it's a little bit harder to visualize, but if you think of the CO2 as like water, right? Eventually, if you fill the entire trench with water, the level of the height of that water will change with time as you fill up the trench. Okay, so we want to find out how quickly the trench is going to fill with the CO2. Right. All right, and then B, let's compute based on our answer for part A. In part B, we're going to compute the time it would take for the height of the CO2 to reach 6 feet, which is the approximate height or average height of a typical worker. Okay. All right, so this is another kind of straightforward application of Reynolds transport theorem. So let's go ahead and get started with that. Okay, so let's do part A first. All right, so part A, we're going to compute the rate of height change, right? Which may seem kind of strange. So you'll see that there's nothing in our Reynolds transport theorem that may give us that explicitly, but it is something that we can actually derive from Reynolds transport. Okay, so let's start there. All right, so let's go ahead and apply our Reynolds transport theorem. We only have one form right now, which is mass. Yep. All right, so we have our accumulation term here, integral of rho v plus integral of rho v dot n hat dA. All right. So in this situation, we have an unsteady case here, right? So we're told in the problem that the CO2 will start to accumulate in the trench. And so that's kind of a keyword that tells us that, we need to keep the accumulation term, okay? All right, so let's go ahead and simplify this a bit. So, in most situations, unless the problem basically tells you differently, we can assume that the density is constant, okay? And so if we assume the density is constant, we can then pull them out of the integrals, right? So the density is not going to vary within the control volume itself. Okay. Right. And so we have partial t. We can even pull the density out here. Right? So we have density multiplied by partial t of integral of dv. So remember, whenever you have a constant, you can pull it out of the integral. You can pull it out of the derivative as well, because a constant doesn't change within the integral. It doesn't change within the derivative either. Okay. Oh, another thing that I'll do is let's take our inflow and outflow terms and let's replace this with our more convenient form. Okay. Let's replace this with m dot out minus m dot in summation. Right. But in this case, we don't have an outflow, and so let's go ahead and cross this out. And we actually only have one inflow here, so we're just going to subtract an m dot in. All right. So now we got to do a little bit of math here, although not really. So we have a blank integral here. So we have an integral of 1, essentially, of dv, right? So integral of dv just by itself just gives us the volume. Okay, so we plug in for that. We get rho multiplied by the partial derivative with respect to time of the volume. Okay. Specifically, this is the volume of CO2 within the control volume. Okay. Right. So remember, the subject of our control volume is the CO2, right? And so the volume there refers to the volume of CO2. Okay. Minus m dot. Before we forget, all this is equal to 0. So don't forget that. Okay. All right. So next, let's go ahead and plug in for the volume, right? So the volume of this trench here, we have just a rectangular box trench, right? So the volume of the trench here is the product of the length multiplied by the depth multiplied by the height. Okay. And let's go ahead and plug in for m dot in as well. So m dot in, remember, is the density of the CO2 multiplied by the inlet area multiplied by the velocity. Okay, so we plug both of those in, we get density times partial derivative with respect to time of the length times d times h minus density an v n equal to 0. Okay. All right, so both terms here have the density, so let's go ahead and cross that out. Okay. Okay, now we need to work on this volume term here, right? Because we have the time derivative of L times D times H. Okay. We have to use a little bit of intuition here, a little bit of ingenuity, right? Okay. So based on what we know from the problem, right? We know that CO2 is going to fill this trench and eventually the level of CO2 is going to rise up, right? But based on kind of the direction of gravity, so gravity in this case is going this direction, right? So as CO2 fills the trench, right, it's going to fill an entire layer at the bottom of the trench first, right? Right. So it doesn't make sense for CO2 to fill the trench and just kind of take up just like a region over here, right? That doesn't make sense because that doesn't work. That's not where gravity goes. And so CO2 is going to go fill the entire bottom layer first and then kind of build up from there. Okay. And so in that sense, right, when we're computing this derivatives here, this derivative with respect to time of L times D times H, right, where L is the length, D is the depth, and H here is the height. Okay. So because it's going to fill out the entire layer first, right, the length and the depth dimension are not going to factor in, right? So it fills those directions much more quickly than it does the height. And so in that sense, what we can do is we can just factor those out of our derivative here and really just concern ourselves with the rate of change of the height. That's going to be much more easily observable than the other ones because the CO2 fills the length and depth much more quickly. Okay. Okay, and so if we do that, we get L times D. We pull that out of the derivative. Okay. Right, and then we have the partial derivative of H with respect to time. Okay, minus A in V in of the CO2. Okay. Right. The product of A in times V in here, remember this is our volumetric flow rate. See? All right, and we have the length and we have the depth. We know those given to us from the problem. And so we can solve for partial h partial t, which, if we go back to what we were looking for to begin with, that's the rate of change at which the height of CO2 is changing with respect to time. Okay. All right, so we solve this equation here for d partial h partial t. We get partial h partial t is equal to q CO2 divided by L times d. Okay. Right, so we plug in for everything here. So Q here, remember this was 10 feet cubed per minute. L here, this was 10 feet. The depth here was 5 feet. Okay. Plug all that in, we get a rate of 0.2 feet per minute. So every minute you stand in that trench, or every minute the worker stands in that trench, the level of CO2 rises by 0.2 feet, which is what? That's a fifth of a foot. A little bit less than 2 inches per. A little bit more than 2 inches per minute. All right. Any questions on how we got that? How we got that there? Okay. All right. So then let's do part B. I do have a couple more examples, but it's a little bit awkward. So let's do part B and then we'll end a bit early today. Okay, so part B asks us, now that we know the rate at which the height of CO2 is gaining, let's find out how long it takes for the height of CO2 to reach 6 feet. So remember, for this problem, we're assuming that at the very beginning, no CO2 exists in the trench at all, right? So we're starting at a height of 0, okay? And so in order to reach 6 feet, we're just simply going to take 6 feet divided by the rate that we just computed in the previous part, 0.2 feet minute, okay? All right, you can see here the feet are going to cancel out, and so and the minute from the bottom just comes up to the top. So this gives us our time. All right, so we have just 6 divided by 0.2. That there is 30 minutes. Which is not a lot of time, right? And so that's dangerous. And so you would probably take this information, you would go to your contractor or your manager and say, hey, we need a vent here. We need something to pump out the CO2 from this trench. Otherwise, our guys are going to suffocate down here. Typically not a good thing. All right, any questions on this? Okay, all right, so let's call it here. So when we come back on Tuesday, we will do problems with moving control volumes and forming control volumes. Then we'll move on to momentum and energy. Okay. So I'll grade your guys' exams tomorrow and Monday, so I should have them back to you guys on Tuesday as well. So if you want to pick up your exam, you can come on Tuesday, but the score should be on Canvas sometime before lecture. All right, so thank you guys for coming today. Hope you guys have a good weekend, and I will see you guys on Tuesday. Next homework will be due next Sunday. Yeah. Oh, yeah. Yeah, you need it. Otherwise, it's yeah, I'm gonna post the homework read today.
Okay. Okay.
Hey, Chris, I'm really good. What's up? Okay, yeah. Yeah, no, great question. It's yeah. Oh yeah, that's one way. And so the example that we didn't get to do today is actually an aircraft engine. So an aircraft engine is attached to an airplane, right? And the airplane's moving. If you want to do an analysis on this, you have to account for the motion of that airplane as well. So that's essentially going to affect how you observe the velocities coming out. The velocities coming in and out, they're affected by the so
We're looking at stationary kind of.
exactly. Yeah.
The moving ones ground. Like literally, you should look into space.
Exactly. So yeah, every velocity that you're going to compute here is going to be a relative one.
Oh, okay.
Yeah, no problem.
But the final is going to be like roughly the same like amount of questions.
No, final will be longer, but you'll have the entire class session too. So you'll have 3 hours.
So, yeah, I was thinking a long time, so it was like an exam.
Yeah.